Focusing on the permanent magnet machine, how do we push those efficiencies as far as we can? How do we reduce those disadvantages as much as we can? First thing we're going to look at is a newer type of rotor topology. That's going to be a Halbach array rotor topology. So it's how we configure the magnets on the surface of the rotating portion, the rotor of the permanent magnet motor. So a traditional rotor is going to be radial magnets. So it's going to be radially oriented with north and south magnets alternating around the circumference of that magnetic rotor. So we're going to compare a 30-pole machine with 45 slots. In our comparison here, the stator geometry was held constant through all cases. And the three types of magnetization patterns we're going to test are a parallel, which you see on the screen now, a 4-segment Halbach, which is all wedge-shaped, and then a 4-segment Halbach with parallel and wedge-shaped. And you'll see what I mean by parallel and wedge shapes as you see those images on the screen in the next couple slides. All the magnets in the model are Racoma 35E grade permanent magnets, unless we know otherwise, with a BR of 1.17 Tesla and the HC typical of 860 KAM. So looking at just the parallel magnet configuration, you can see that the magnet shape is controlled by MW, the magnet width, which is shown on the screen, and also MT, the magnet thickness, which is shown on the screen on the image. The rotor outside diameter is held constant through the studies. So let's look at some of the results from this analysis, looking at the parallel magnet's torque. We can see that the torque is primarily driven by magnet width, so wider magnets have more flux, thus they have more torque. Deeper magnets are more limited in their ability to increase the torque because we're trying to get more flux at the air gap with the width of the magnet. And the torque ripple is very sensitive to magnet width and insensitive to magnet thickness as a resultant. And we can see the images here, just some comparisons of using different width magnets and different thickness magnets. Now, let's take a look at the Halbach. If you're not familiar with a Halbach topology on the surface or circumference of a rotor, we're inserting magnets, tangent magnets, we'll call them tangent magnets, between the radial magnets of the rotor. So instead of just a north-south orientation around the circumference of the rotor, I'm going to insert a tangent magnet between, as you can see on the screen in front of you. So the first Halbach design we use has wedge-shaped magnets, so every single magnet has it's a wedge, it's an arc, it has a degree. So this way we fill all the air gaps between the magnets with magnet material. So the magnet angle is varied to look at how the pole and transition magnet sizes affect torque and torque ripple. The pole magnets are shown in gray on the slide, so you can see north-south in the section of the model, and the tangent magnets are shown in white. So taking a look at the torque results of the two, we want to know what's the best sizing we can have. So you can make those tangent magnets wider, you can make the radial pole magnets wider, or you can make them deeper or not also. So we can do a lot with the shape, overall volume of both the radial and the tangent magnets. So the graph at the right will use normalized results based on the ratio of the pole magnets. We call that SPM at the outer radius of the rotor and the arc length divided by the pole pitch. We call that SPP, just for clarification on those slides. A ratio of 0 would be only tangential magnets, and a ratio of 1 would be only pole magnets. Obviously, we don't want 0 or a 1. We want to figure in the middle. So looking at the graph on the right, we can see that the maximum torque is achieved when the arc length of the pole magnet is roughly 1/2 the total arc length of the magnetic pole. In the bottom image, you can see SPP, the pole pitch, and the SPM, the overall width of that pole piece, that magnet.